To access your iReady lesson, simply go to myaps.edu and click on the iReady icon. If you haven't already done so, please install the login extension. Once you're in, you'll want to click Math, since that's what we're doing today. And you'll see two types of lessons as usual, My Path and Teacher Assigned. Try to do both, but if you only have time for one, try to prioritize the Teacher Assigned lesson. From this point onward, you know the routine. Hi students and families. Just a quick announcement here. The fraction tiles I use in this video are actually from the dollar store. And the reason I'm mentioning this is because if you're able to play with something like this in person and explore how fractions interact with each other, it's priceless. But the investment is only $1. That means that for the price of a Coca-Cola bottle there, you could take home something. And even if you only spend 5 minutes on it together, or roughly the same time it would take to drink one of those Coca-Cola bottles, the student will have already developed a much better sense of proportion and will have started to become more curious about mathematical phenomena, which they're going to be held accountable for in the coming grades. So even if you only end up using these for a few minutes and putting them away for another 6 months, you'll have accomplished something very special because you'll have interacted with important mathematical concepts and applied physical manipulatives into your discussion. Also, when you bring home a pizza or make a pizza, cut it together as a family and talk about how you're cutting it. Are you cutting it in eighths or sixths or twelfths or some other division? The student can use that opportunity to understand why the pizza is being divided the way it is, or the cake or the pie or whatever it is, and talk about the type of division it is. Talk about whether it's in fourths or sixths or eighths. Apply the fraction number while you're talking about the reason you're cutting it up that way. And don't forget where else we use fractions. When we talk about clocks, for example. When we say half past, or a quarter past, or a quarter till. Any opportunity we can think of to incorporate fractions into our daily discussions as a family, give the children a better sense of what it means to divide a whole into fractions. Here's some toy money, which I also bought at the dollar store. And the reason I'm bringing this up is whether children are making use of real money, or playing with toy registers of money like this, or practicing more sophisticated transactions in games like Monopoly, they're developing sophisticated concepts of multiplication and fractions. For example, remembering that you need 4 5s to make a 20. Every time we do that, we're using multiplication. Remembering why we call quarters quarters, because you need 4 of them to make $1. Each one is worth a quarter or a fourth of $1. Just as a dime is worth a tenth of $1, so you need 10 of them to make $1. The word dime, interestingly, is related to the Spanish word décimo, meaning a tenth, by the way. And a penny, or 1 cent, is worth 1/100th of $1. Hence the word cent, like Spanish cien. So whatever activity you plan, be it with real money or toy money, it's beneficial for math practice. I want to look at some flat tiles here. Let me just make them a little flatter. There we go. All right, so what I'd like us to think about is the way we've done multiplication a lot this semester. Here we have 3, but we see 3 2 times. So 2 times 3 is clearly 1, 2, 3, 4, 5, 6. But I want us to think about the way we look at floors which have been tiled with squares, which would make each one a square foot. Similarly, each of these tiles is an inch this way and an inch that way, which makes each one a square inch. Now, if we put these together, knowing that each one is a square inch, we don't just have the number 6 here to say that there are 6 tiles. We have 6 square inches. 1 square inch, 2 square inches, 3, 4, 5, 6 square inches. But we can measure it the same way we do with a lot of the multiplication exercises we did before. 2 inches this way, multiplied by 3 inches this way. 2 times 3 equals 6. So it is 6 square inches, in addition to the fact that we can just count 6 tiles, and we know that each tile is 1 square inch. Now, it might not seem like much of a difference at this point because we only have 6. But if we have a much bigger number of tiles here, such as 4 going this way and 7 going this way, it's much quicker for us to say, well, what is 4 times 7 than to count to a much higher number, like 28. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Now here we've practically doubled the number, which will make it very time-consuming to count each individual tile. But if we simply look at the fact that this direction is 6 inches and this direction is 9 inches, we can simply multiply 6 by 9 and know that it is 54 square inches. Now, how is this different than simply multiplying? Well, in terms of the kind of work we have to do, it's not. It's just as easy as multiplying, or just as hard. But in terms of what we can do with it, it's different. If we're installing tiles on a floor, and we know that we would need 54 square inches, maybe in a dollhouse, or 54 square feet in a regular house, we would know how many tiles to buy. And that's how we deal with measuring what we call area. Now, what if instead of putting down tiles, we just wanted to build a fence around this? Well, then we wouldn't be multiplying, we would just be adding. We would have 9 inches going this way, and since it's a rectangle, also 9 inches going this way. We'd have 6 inches going this way, and since it's a rectangle, also 6 inches going this way. So basically, we'd have 9 plus 6 plus 9 plus 6. So we'd need something like 30 inches of fence. Or if these were as big as real kitchen tiles, more like 30 feet of fence. Now, speaking about square inches and square feet, we often use the word square in multiplication to refer to a number times itself. Remember that if something has the same width and length, you refer to it as a square. So this is a square centimeter right here. But we could do it with bigger numbers than just 1. Here's regular 3. Here we see 3 2 times. Here we see 3 3 times. That is 3 times 3, a number times itself. What does that give us? 9. So this gives us 3 centimeters of width and 3 centimeters of length. 9 squares, each 1 square centimeter, makes for 9 square centimeters. Because 3 times 3 equals 9, and also because we have 1 square centimeter, 2 square centimeters, 3 square centimeters, 4, 5, 6, 7, 8, 9 square centimeters. This doesn't just apply to 3, but any number. Here we have 4, and 4 times 4 is 16. So here we have 16 square centimeters. Here we have 5, and 5 times 5 is 25. So here we have 25 square centimeters, and so on. Now what about when we have a number times itself, like 3 times 3, times 3 again? Now we have a width of 3, a length of 3, and a height of 3. 3 times 3 times 3 is 27. So this is 27 cubic centimeters, which looks a little bit like a Rubik's Cube. Now what do we use things like cubic centimeters and cubic inches and cubic feet for? Well, let's say you want to build a hot tub, a perfectly square hot tub. You'll want to be able to measure how much space it takes up. This way you'll know how deep to dig. This is called measuring the volume, which is kind of like the three-dimensional version of measuring the area, like we did when we measured the floor tiles earlier. And of course you're going to want to know your multiplication well to deal with this. 2 times 2, or 2 squared, is simply 4. And that's very easy to count. 1, 2, 3, 4. 2 times 2 times 2, or 2 cubed, also isn't too big or scary a number. 1, 2, 3, 4, 5, 6, 7, 8. But the bigger the number, the harder it gets. Let's try 5 times 5, or 5 squared. 1, 2, 3, 4, 5 times 5. Well, we know we have 5 going this way. We want to make sure we have 5 going this way also. Five square, equaling 25, took me a lot longer to count to than 2 square, equaling 4 did. And the same is true when I try to cube it. 2 times 2 times 2, or 2 cubed, is simply 8, which is very easy to count to. But 5 times 5 times 5, or 5 cubed, takes much longer to count to, because it equals 125. And this is just 5 cubed. What about when you're dealing with much bigger numbers, like 53 cubed, or 537 cubed? If these are big construction-style bricks, you better know the right number to buy, or you're either going to waste a lot of money or have too few for the job. It's time again to talk about fractions. Let's recall again what halves are. Halves are when we break a whole into 2 parts. And when we break something into 4 parts, it's called fourths, or quarters. Now, it's no coincidence that when we talk about money, we refer to 4 of these things right here as quarters. Why? Because you need 4 of these to equal 1 of these. These are worth a fourth of a dollar, a quarter of a dollar. So, in terms of fractions, a dollar is a whole dollar, and quarters are a quarter, or a fourth of a dollar. You need 4 of these to equal 1 of these. Another interesting fact is that you need 10 dimes to make $1. And the English word dime is related to the Spanish word décimo, meaning 1/10. Now let's look at fourths, or quarters, just a little bit more closely. Recall the relationship of 4 to 8. 8 is twice as big as 4. However, it's the opposite with fractions. An eighth is twice as small as a fourth. And thus you need 2/8 to equal the size of 1/4. Also, 16 is 1, 2, 3, 4 times bigger than 4. But you need 4/16 to equal the size of 1/4. Now let's look at 3 and a third again. You need 1, 2, 3, 4 times 3 to make 12. And similarly, you need 1, 2, 3, 4 twelfths to equal 1/3. Similarly, you need 1, 2, 3 times 4 to make 12. And likewise, you need 1, 2, 3 twelfths to equal 1/4. This is why a third is bigger than a fourth. You need 4 twelfths to make a third, but you only need 3 twelfths to make a fourth. Just as 3 needs to be multiplied by 4 to make 12, while 4 only needs to be multiplied by 3 to make 12. 4 is a slightly bigger number than 3, while a fourth is a slightly smaller number than a third. The real numbers 4 and 3 meet at 12, and the fractions, a fourth and a third, meet at a 12th. Well, now seems like as good a time as any for a word problem. This one is from iReady. Third graders at Brown Elementary School are raising money for the school library. The goal is to raise $250. They raised $9 each day for 8 days in a row. Well, if they made this much every day, and there were 8 days like this, then we need to see this 8 times. Okay, so here we see 9 8 times, which means that for each of the 8 days, they raised $9. Now we're going to need to regroup these a little bit more neatly if we expect to compare these with this. So, 9 times 2 is 18. What that essentially means is I take 1 away from this 9 to make it an 8 of the 18, and then it combines with this 9 to make a 10 bar. I now have 18. 9 times 3 is 27. Take 1 off of this 8, combine it with this 9 to make another 10 bar. And now I have 27. 9 times 4 is 36. So I take 1 off of this 7, combine it with this 9 to make a 10 bar. Now I have 36. Continue the process for each of these days. Until I have 72. Now, what is the difference between 250 and 72? This is much easier to count. Well, in order to make 72 match the first of these hundreds, I'll need to have 2 more tens and 8 more units. There's 28. I'll need to combine that with the next 100, and then with another 50 to match the 50 that's here. When I combine these 10 bars, the 50 becomes 70. The 8 units are still 8 units. So the difference between 250 and 72 is 178.
Okay, so that's the end of the video. Like and subscribe.